To chair this session, we have Professor S.K. Prasad from Vidyavartaka College of Engineering, Mysore, as well as member of the International Networking Committee of Geotech Asia 2025 and National Executive Committee member of the Indian Geotechnical Society. To co-chair the session, we have Professor Akansha Tyagi from IIT Roorkee and member of the Technical Committee of Geotech Asia 2025. To take up the proceedings, I invite the chair and the co-chair.
Thank you very much, madam. Good morning, everybody. We have three very important lectures in this session, and I first of all wish to thank Geotech Asia 2025 for giving both of us the opportunity to chair this session. So, it is total duration is 1 hour, in which each of the speakers will have 20 minutes. So I request the speakers to keep up with their time. The first presentation will be a special invited lecture by Professor Cheong Siu Chen Darren, who is the president of Geotechnical Society of Singapore. And he is going to make a presentation on geophysical methods in tunnel look ahead and deep soil mixing. May I invite Professor Cheong Siu.
Thank you, Chairman. Good morning, everyone. I'm Professor Darren Chen of the National University of Singapore. I'm also here representing the Geotechnical Society of Singapore for this invited lecture. The topic I'll be presenting is the application of geophysical methods for tunnel look-ahead investigation. This tunnel look-ahead technology is the result of a collaborative research project with the Land Transport Authority of Singapore. The key contributors to this project include Mr. Tan Yun So, Professor Elita Lee, and Professor Arthur Cheng, who were previously part of this research team at NUS. So this is an overview of what I'll be covering today. I'll start with the motivations behind our research, and then go into the key challenges we aim to address. After that, I'll walk through with you on the research methodology we used and wrap up with a few case studies showing how the approach was being applied in practice. In land-scarce Singapore, underground space has become a vital asset for ongoing urban development. Over the years, we have buried key infrastructures like utilities, roads, subways, and highways all below ground. As the subsurface becomes more crowded, it brings new challenges to the planning and carrying out of future tunneling projects. This is a typical tunneling boring machine, or TBM. At the front is the cutter head, which breaks through soil or rock during excavations. Behind it are the supporting systems that keeps the machines running smoothly, and this remains accessible throughout the tunneling process. Tunneling is often compared to digging in the dark. We usually don't know what lies ahead. Excuse me. Until the TBM reaches to that particular location. And this uncertainty is made worse by the natural variability of the ground conditions. We may face challenges like water ingress, boulders, soil rock interfaces, or even unexpected encounters with old abandoned structures. The tunnel look-ahead technology that I'll be sharing today is based on seismic reflection methods. It works a bit like bats, okay? Navigating in the dark they send out sound waves which bounce off objects and return as echoes, helping them sense their surrounding. Similarly, we emit seismic waves from the tunnel face, and these waves reflect off underground features like voids, boulders, or changes in geology. And these are all being picked up by our sensors, our geophones. And this gives us an early warning of the potential hazards before the TBM even reaches them. So let us just wait for a while. Great. Fingers crossed. Okay, so with that in mind, let's move on to the research methodology. Earlier, I mentioned how bats use sound waves to navigate. Similarly, in tunneling, we introduce seismic waves using either active or passive methods. Active methods involve generating waves manually, such as striking the tunnel lining with a hammer. Passive waves, on the other hand, are being generated and relied on ambient vibrations, like the noise produced by the color head during the tunneling as the wave source itself. Each of these approaches has its own advantages depending on the site conditions and operational constraints. This technology, we call it as a smart boring system. So anything new, we just put a smart word in front. So it combines the data collections inside the tunnel, the numerical simulations, and the wave signal processing to detect the size, the location, and the stiffness of the potential obstacles up to about 30-40 meters ahead of the color head. And the key benefits include less exploratory boreholes needed, early planning and actions on potential obstruction risks, and improved safety for workers and equipment through better foresight and preparedness. For the data acquisitions, we place geophones in a straight line along the tunnel wall. Just try and use the laser pointer. Can you see the laser? Okay, never mind. Okay, so you can see from the top middle and the left figures, they show the geophones being laid in a straight line along the tunnel wall. And in active seismic acquisitions, we create waves by striking the precast tunnel lining with a sledgehammer, which is at the bottom center picture here. Right? So these waves travel through the ground and are picked up by the geophones. And the further is the geophone from the source, the later it records the signal. Okay? And in passive seismic acquisition, like the one that you can see at the bottom right-hand side, the cutter head turning, there is no need for an artificial source of the wave. Instead, geophones continuously pick up the natural vibrations generated by the tunnel boring machine as it moves forward, and using that noise as the wave source for our analysis. We also run numerical simulations to model how these seismic waves travel. Since the TBM front section is hard to access, the closest we can place an active source is about 21 meters away behind the cutter head. In the simulations, imagine an obstruction 70 meters ahead of the cutter head, as you can see from these 3 red spots at the top. And when the sledgehammer strikes the tunnel lining, the waves travel along the lining, okay, on the top right-hand side, and through the soil as well, Okay? Because the tunnel lining is stiffer than the ground, hence the waves tend to travel faster along the line, the tunnel lining, okay? As shown here. And when these waves hit the obstruction, as you can see right now, okay, some of these waves bounces back, while the majority travels forwards, okay, and upwards. And the reflected waves is slowly being picked up by the geophones being placed along the red line array over there. Okay, so for active seismic source, the raw data tends to be relatively clean and straightforward to interpret, as you can see from the on the far left hand side. In contrast, the passive seismic source, the data is more complex, more noisy, as you can see at the center here. And to extract meaningful signals, we use an interferometry process which leverage the consistent time intervals in order to enhance our signal quality. And after this processing, the resulting signals becomes much cleaner and easier to analyze, as you can see on the far right hand side. So now let me explain how we use semblance calculation to isolate signals coming from ahead of the TDM. Since the geophones are placed and arranged in a line with known spacing, seismic signals in front of the TBM, they reach them one after another. Okay, so the signals will first reach geophone R1, and as you can see also on the bottom right hand side, R1, and then subsequently R2, and so on up to R24, which is the last geophone that we have. And this predictable time delay allows us to align and correlate the signals and enhancing the detection of reflections, specifically from the tunnel phase ahead. Okay. So for the semblance, this time around a 2D semblance analysis, we begin by scanning across a range of possible velocities to generate this semblance value. Okay. So we start off with a gentle load in our time versus our distance plot. Okay. And this process will produce a second plot of time versus slowness. Okay. And the slowness is the inverse of velocity, that's all. Okay, so it's nothing new. Where these different colors would indicate the strength of the seismic thickness. And once we are able to identify the prominent peaks in this plot, which is then we can determine the velocity of the propagating waves. And using this velocity along with the measured travel time, we can accurately infer the distance of the obstacle away from the other head, how far it is. The next important aspect that I would like to discuss here is that the obstruction is not necessarily always right in front of the TDM. They may be positioned at an angle relative to the tunnel axis, which over here we call it as aperture. To understand this effect, we conducted several simulations with obstacles placed at different angles ranging from a negative 20 degrees to a positive 20 degrees. Okay. As you can see from the animations of the three dots flying across. Right? So in the graph, as you can see on the right hand side here, the distance that we obtained, okay, from our signals, the distance between the color head to our geophone is 20.96 meters, which matches closely with the actual distance of 21 meters, as you can see from the left hand side. Okay, so for an obstruction located 15 meters, 15 meters ahead of the color head, or in total 36 meters from the geophone array, we can observe that the semblance signal is the strongest at 0 degrees. Okay, the highest peak, as you can see at the top right hand side. And 0 degrees means that the obstruction is right in front of the TDM. And this signal starts to decrease, okay, in strength and decrease in clarity as the aperture angle increases in either direction, okay, in either sides. And this means that the accuracy of the distance estimations becomes less and less certain, okay, with a greater aperture angle. So in order to improve the accuracy, we recommend continuous data acquisitions as the TDM advances. So this allows for the confirmations and refinement of the obstructions locations over time. Another effective approach is to install dual phone arrays on both sides of the tunnel, as you can see on the top left-hand side. And this dual array setup offers that additional perspective to enhance our data quality if we need to. We can apply Bayesian calculations to further refine our estimates. And by combining these multiple measurements at different dates, at different times, through superpositioning, then the resulting probability distribution peak, as you can see at the bottom right-hand side, indicates a more precise and reliable estimate of the obstacle's position, and thereby increasing our confidence in the estimated distance. So now let us move on to review several case studies that demonstrates the application and the effectiveness of these smart boring systems in a real tunneling projects in Singapore. So in the first case study, we focus on detecting abandoned piles about 40 meters away ahead of the TDM. So with continuous monitoring, we tracked the obstacle as it got closer and closer to our tunnel face over time. And this helped us to identify two groups of disused piles, one which was previously unknown to both the Land Transport Authority, the client, and the contractor. And this shows how the smart boring system can in fact help to uncover hidden substructure hazards that previously we would have never been able to perform. Although no obstructions were initially reported, our continuous monitoring gave us that strong confidence in the presence of these disused pile groups. Following up investigation did confirm piles at ring number 51, as you can see over here, and this proves the smart boring system's reliability. We also found that the penetration index that we came up here with the calculations closely matched the detected pile locations, and this reinforced our results and validated our estimates of the distance away from the function. So beyond the piles applications, the system over here is also able to identify a soil rock interface at ring number 112, as you can see at the bottom right hand side. And this again shows its ability to detect different types of subsurface features. Some cartoons here for you. Okay. And this brings us to our case study number 2. Traditional site investigation has been helpful, and it provides the ground profiles. However, they only provide that at those specific locations of the boreholes that we conduct. Okay? But the soil strata and the rock depths can vary significantly between our boreholes. Okay? And in this case, we have successfully detected the soil rock interface at around ring number 60, which is right here. Okay? And this was later confirmed by the analysis of the mark density being derived from the excavations and the TBM penetration indices, okay? As you can see from the green arrows here. Okay, our final case study covers the tunneling beneath the pile foundations of a 3-cell box cupboard at Changi Airport. Based on as-built drawings and the magnetometer survey, the piles reached a depth of 40 meters deep, while our tunnel crown was at 15.9 meters. So that leaves a tight clearance of about just 1.9 meters. So using our smart boring system, we ran a Bayesian analysis, and that showed a low probability of any obstructions along the TBM path. And thanks to this, the tunneling went ahead confidently and smoothly without any issues. Yes, yeah, no problem. Okay, so in summary, our smart boring technology provides a non-intrusive and cost-effective geophysical solutions for geotechnical applications such as in tunneling. This technique causes zero interruptions to our TBM operations. The TBM operations can continue to run as per usual. There is no cutter head access required, no drilling, probing. It is able to offer near real-time reporting. It has a long detection range of 40 meters, high detection resolution of 2 meters. We get precision measurements on our detections, okay? And it is most importantly EBM independent. Okay? Ultimately, the smart boring helps to reduce project delays, minimize equipment damage, and lower overall costs, thereby making tunneling safer and more efficient in a highly urbanized environment. So I would like to express our sincere gratitude to our partners from NUS, from the government agencies and the contractors. And thank you so much for your attention. I'm happy to take any questions that you may have. Thank you.
Thank you, Professor for an excellent presentation on smart tunnel boring with 3 case studies. So you finished well on time. There can be 1 or 2 questions. So from the audience, if there is any question, it would be very nice. Well,
thanks for interesting presentation. I am Suyesh Trivedi, Executive Director with Mumbai Metro Rail Corporation. Yesterday only our line started, and day before it's a fully underground line from Mumbai that has been inaugurated by Honorable Prime Minister day before yesterday. So I have few questions. Like you have told this technology, seismology technology, there are other technologies too to predict the ground ahead. So what is your observation, which one would be best available as on today? Because what I have felt with this technology is there is this problem of interpretation. Interpretation is the most important thing, and professionals are not available in the industry to correctly interpret these waves and analyze all these things. So there are people in India as well, but we are not getting good satisfactory results so that we can conclusively say what is ahead of us. So based on your experience with the Singapore Metro and with your own academic what would you recommend to us? Because we are going ahead with another huge project in Mumbai that's again underground. So if you can throw some light on that, please. Thank you.
Yeah, thank you so much, sir, for the questions. Indeed, that you have spotted it correctly. Geophysical methods, for example, geophones, it appears to be like off-the-shelf technology that you can just buy and use it. However, the challenge indeed, as what you have mentioned, is the data analysis, is the data interpretation part of it. And that was also our challenge back then. So if you ask me what is my recommendation, I think it's about building that expertise. For Singapore, we are more than happy to support, to assist on how that these technologies could be used more widely in overseas. And I mean, being from NUS, from the university, we are more than happy to be able to see our research being used across, right, in different countries. So, yes, indeed, that was, the challenge. However, I think it came to a point whereby so the codes itself on how to interpret were actually written by ourselves, right, the codes. And we did a lot of trials before really going up to do in real tunneling projects, because when you go to the real projects wise, then it's either you make it or it's either make or break, right? And if you break, then nobody is going to be confident about this particular technology, right? So we were very cautious, and the thing is that the contractor, the client, kind of look at us like we are being contracted, like we are being paid by them, but we are not. I mean, we don't get a single cent from them. But when we do it because of passion, because of the love of research, and they require us to report to them every few hours, and we had to really be on our toes to really detect. And fortunately, for these 3 case studies, we were able to do it very well. I'll have to say that the success of this method itself, as I mentioned just now, is about the change in the stiffness of the ground. So if you are looking at two mediums, two soils types, whereby it has about that same stiffness, then it will be very difficult for us to identify the differences between them, because the waves travel just as if that the waves do not stop and say, this is clay, this is sand. But through the stiffness, the waves travel at different speeds, and that's how we detect the differences. So there's no rocket science. However, in terms of how we interpret the data, the signals itself, that is, and also filtering away the noise and keeping the signals, these are all perhaps more of an art than a science. But I think that we managed to nail it. Well, I'm more than happy to discuss. Yes, I'm very
Thank you, Professor. So,
Thank you, Professor. And now to present a memento to the speaker, Professor Jianxiu Chen Darren, I request the chair and co-chair.
Yes, a quick one, since I'm a practitioner also in deep excavations. The question is, can you bring that technology to small drilling? And the analogy is with probability of a ship hitting an obstacle is much less than 1,000 ships moving in different directions. So if we can adapt it or adopt your system, think about it for future, to drilling anchors and going 25 meters in all directions on a deep excavation. And many times I faced and grouted archive rooms of a hospital. So that would be, I like to hear your answer. That would be a good thing.
Yeah, thank you so much, Dr. Paulus, for the suggestions. We will continue to push forward and to be able to try and identify smaller and smaller objects, as best as we can. Thank you so much.
Thank you. Request the chair and co-chair to present the memento to the speaker.
we have the next presentation, invited lecture 14 by Professor Dimitrios Zekos from University of California, Berkeley, USA. He is going to speak on a big data approach to regional resiliency against co-seismic landslides. Over to you, Professor.
Great. Can you hear me well? All right. Thank you very much for the opportunity to talk to you today about our approach to handling co-seismic lands. Over the course of preparing for the presentation, I started shortening the scope of the presentation. At the beginning, I was also planning to talk about precipitation-induced landslides, but focus on the seismic. So, when a major earthquake happens in a mountainous area, there's significant number of landslides happen. And there have been a number of cases related to this. More recently is the Gorga earthquake in Nepal that is nearby, that there were more than 25,000 landslides associated with that earthquake. 2 years later, we had the Kaikoura earthquake in New Zealand, where we had more than 40,000 landslides introduced by that earthquake. 2 years later, there was a combination of monsoon and earthquake loading that caused significant landsliding in Hokkaido earthquake. These are areas that have worked with. But also nearby where I work at Berkeley, we still have the images of the 1994 Northridge earthquake in California that caused lots of lands. So when you're seeing this scenery, and of course it's an unfortunate event, but there is a tremendous opportunity to learn from this type of land. We have a full-scale experiment by nature in terms of testing our entire topography. However, our approaches as in geotechnical engineering are not scalable to really address this type of problem. We know very well how to really characterize each of those individually, but we don't have techniques for site investigation and site characterization to really look at the full extent of the data we have from nature. And when we're talking about the resiliency of our communities broadly, but also specifically for landslides, I don't think we serve very, very well our communities when we actually, after the fact, were able to go back to the location where the landslide happened, drill our boreholes, do our cross-sections, run our models, and really explain why the factor of safety was one or the other. What we really want to achieve from a resiliency perspective is really to be able to predict landsliding before it happens and over large areas. That has to be our goal. And when I'm talking about predicting landsliding over large areas, I'm talking that ideally we'll be able to predict the exact location, the probability of occurrence, because there's going to be uncertainty, the size of the landslide, and of course the consequences. Because whether it's big or small landslide, where it is exactly matters, right? And so that's our goal. And some people may think that goal is unrealistic. I believe strongly that with the advances we have in technologies and modeling, we will be able to achieve this. Not so distant. So this is a framework that maybe you have seen. This is a classic framework we're using for really what we call the landslide life cycle. And it starts with mapping, being able to map the landslides and monitor the geologic environment, then trying to take lessons out of these landslides by doing some calculation. Then of course understanding that once a landslide triggers, it may move a lot. And so we talk about the run-out analysis. And then if we understand all of this with the system, we should be able to do predictive modeling throughout our regional system and identify the weakest spots and fix those first. Fix the ones that have the worst consequences. And then we go back with monitoring, really do it. So I'll try to show some applications of this type of life cycle that we have here for one study area. Now we have applied this to a number of areas, Nepal, New Zealand, in California, as well as Greece. I'll focus on Greece because I'm from there, and I have a number of examples staying on one side. So I'll start with mapping a little bit. So to describe what happened here, I'm going to be using Lefkada Island in Greece. It's located on the western side of Greece, maybe you can see it with the bullet. And it's one of the most seismically active regions in Europe. There is a devastating earthquake every about 18 years, going back to the 15th century. And that area is really primarily covered by limestone formations. And it's a very actively sheared, subduction zone. There's actually a transform fault in that area exactly. And the limestone is very, very heavily sheared. So what you have is steep slopes, sometimes as vertical as 90 degrees, so basically vertical, as steep as 90 degrees. But when you look at the rock itself, you can see that it's very, very sheared, brecciated sometimes, as mentioned, and, but it stands there. But of course, when the earthquake happens, there's going to be damage. And so, in 2015, there was a magnitude 6.5 earthquake that occurred, and this is footage from a video collected by fishermen during the earthquake. And what you see is basically what looks like a battlefield, right? The entire coastline, which is relatively steep and high slopes, has come down. And this is November, so there are no consequences, really. There were not that many people at that time. But this is also a very popular area. These beaches down at the bottom of these slopes are very, very popular in the summer. And this would have been tremendously consequential if this has happened in the summer. And so there was significant landslide along the west coastline, and I'll focus on that in the next presentation. So what we did is we deployed our UAVs and our satellites, the satellite data, we collected satellite data to really understand what happened along the entire coastline. This is about a 20-kilometer type of coastline in this specific application. We have applied it to bigger scales than this. But what you see at the top left is what things look like after 2 days after the earthquake. And you can see the landslides. The whole area was not accessible for actually several months because of the landslide that occurred in that area. But if you were to show up in this area just 5 months later, so not a very long time, a lot of the evidence of the landslide would have been washed away. You will have a very different image about exactly what happened from that earthquake if you just showed up for the first time. I hope you can see it. In this case, it's because of wave action. But in many other cases, it's simply by restoration work, by just trying to rebuild. So by collecting UAV imagery by collecting overlapping UAV imagery, we're able to create from 2D photos 3D models. And I think you may have seen this technology at this stage. This is what we call here structure from motion. And this is a subset of the coastline. It's about a kilometer that you see there. The slopes themselves are about 100 to 300 meters high. They're very, very steep. You're not able to walk on those slopes unless there is a road cut of some sort. But you're able to create a 3D model of the coastline and really look at these landslides just after they happen. That's what we did. Now, we did the same thing also with satellite imagery. Again, you have to use stereo satellite imagery. And we created basically a 3D model of the entire area, not as fine a resolution as the UAV 3D model, but still half a meter resolution, which is pretty good. So one thing why this is important, and it's really a tremendous benefit we have UAV technologies, we're able to see things at a centimeter scale, and it matters. So what you see here is basically we map all the landslides, and it's really important to really create a full data set and inventory of the landsliding that happened here. And so what you see here is basically the mapping that happened in 3D of all the landslides. And it is important because, as you can see in the right picture, there is what we call landslide amalgamation. Meaning that if you're not paying attention and you generally map things very, very broadly, you may call the thing on the right as one big landslide. But in reality, it's not one big landslide, it's actually 6 different ones that all amalgamate. And using 3D geometries, you're able to separate each of those, and it really comes down to understanding what really was the mechanism of the landslide. Whether it was one big landslide or 6 smaller makes a difference from all perspectives. Now, if I have a 3D model after the earthquake, and I have a 3D model before the earthquake, and we were lucky to have that because of the work of the Greek government, you can actually take a difference between the 2 3D models over the entire coastline and create really 3D geometries of all the landslides that happen along the coast. So what you see here on the top and the bottom, at the top is the satellite imagery using the Sensor approach, and the bottom is the UAV imagery. And what you see is basically colors, right? The blue colors represent a loss of elevation, meaning that if I take the difference of the digital elevation model after the earthquake and before the earthquake, I have a lost elevation. Things move downwards and slip. While what you see with red colors is actually where material accumulates. It's where the debris goes. And so for every single landslide that you see here, we can see how much material failed and where it went. And we do this, so we can separate basically for each landslide what we call the source of the landslide and the runout of the landslide. And this is super important from our perspective, from a consequences perspective. We can look at how much sediment is generated, what type of material is being generated, where it's going, how it's washing out, how it's eroded. What I want to emphasize, in case this 2D image doesn't really communicate, is for every single one of these landslides, we have a full 3D geometry of the source and of the source material and how it translated downwards in this type of environment. And so we can use that actually to back analyze in full 3D every single one of these landslides. And so I would like to do that now. And so the goal objective here is not really to analyze just some of them, but all of them, and try to see the trends. So there's a number of ways we've done it. We're doing it in geotechnical engineering. It's 1D, 2D, which is what's commonly done in geotechnical practice, and of course full 3D. And there's advantages to each of them. As you move to the right towards the 3D analysis, you have better mechanism, better math, more robust understanding of how things move. But of course the computational cost is higher. And so there is an advantage doing in 3D, but many times, even a 1D or a 2D model may be adequate. And so we have been working in this, in all the areas we've been working in terms of scalability of computation versus accuracy, the type of quality of data you have. You don't want to apply a 3D model in low resolution data, right? So the data that you collect has to be consistent with your model. For the purpose of this presentation, I would like to show you a pseudo 3D approach that we developed. We developed a script from these calculations. We call it RISTAB, and we have made it available to the public so anybody can use it for free. But basically, RISTAB approach is really a 1D model, very simple, triggering for seismic purposes. But once you form a trigger, once you trigger, we use geomorphic characteristics to form an entire scoop of a landslide from that trigger cell throughout the whole uphill, basically, and create a 3D landslide. And we have checked that model against the full 3D analysis, and I won't bother you with details, but we have the papers that describe that, where you compare this approach to a full 3D analysis. The reason this is useful, at least in my view, is because it's scalable. I can apply, and we have applied this over tens of square kilometers, so I can actually make decision making. While a full 3D analysis over 10 square kilometers, we definitely need supercomputers to do that right now. So what do we do with this technique is we take every single of the map landslides that I showed you before, and really we're trying to see what is type of the triggering depth and the strength of material that will match the location, the volume, and the area of each of these landslides. And out of each of these models, we get basically a best match geometry, as well as an average normal stress and shear stress for the entire landslide. So for the entire landslide, what was the combination of the average normal stress and shear stress that made this thing move? So at the top, you see the outcome of the land mapping, the way I showed you before. At the top figure, the red polygons really show the source. We're going to focus on the source right now because we're doing the triggering of the landslide. And the source is also shown in the lower figure. This is the mapped source. And so then we match our model. It's not going to do a great job, but we can see how great of a job it does. For each of those landslides, we match the model results and try to do as good as a match as we can, and we measure, of course, the error, how well we did. So at the end, you end up with a figure like the one you see on the right, where we have basically the entire landslides mapped along the coastline, a strength estimate for each of those landslides along the entire coastline, and on the end also the number of landslides. So the very last figure shows the average strength estimate as well as the number of landslides along the latitude. Just the major conclusions here in the interest of time. We can see that there are fewer landslides and weaker strengths in different formations. That we know because geology matters. So you see different strength, lower strength in the Ionian limestone versus the Paxos limestone, which is local. That we know. What is more interesting in my mind is within the same geological unit, we we'll see also differences in strength. We find zones within the same geologic unit that are lower strength and have more landslide. And that's great to know. And what was fascinating in my mind when I saw that is that because there was a landslide that had happened in that area from a different earthquake in 2003, the same areas that failed more catastrophically in that earthquake had also failed, and I'm talking about high accuracy now, had also failed in the previous earthquake. So there is a pattern, and nature behaves based on physics, and actually if you collect the data to pay attention to that, we're able to see. So once we have this information, going back again to each landslide having a point, we can start looking at regional strength estimates that are based on these landslides. And so what we're able to see is different areas that really have the same strength. So what you see in the figure here for the green cluster is points. And every point that you see there is one landslide. We have made no assumption of cohesions and friction. We have used no laboratory tests to derive it. Although I have to say for our study we did also collect field lab data for this. But what you see in the figure on the right is a more Coulomb strength envelope, a yield for that cluster, for that area within the same geologic unit. While another one will have a different strength. And we're able to see that region. And that I think is very, very strong. And very exciting. Now moving on to that, once we have a landslide that has been triggered, that landslide is going to move downhill. And that is important from a risk perspective because some communities are not threatened by failing themselves, but actually from something that's coming from above. And I know I have my Nepalese colleagues here, and I know they know that very, very well. And so it is really important to understand really how far the landslides will move. And once we have mapping of the source and the runout, we're able to calculate the full 3D trajectory on average as well as the distribution of each of those landslides. And what has been done for many, many years, and we have done this year for fun, it was just to regress the data and find how far will a landslide move and do a regression equation. And you can see that if you will do that, you will see that the size of the landslide matters, the slope inclination of the landslide matters, as well as the height of where it is matters. And so that's a regression equation. And there have been so many of those in the literature, and of course we did it. The problem with these approaches is that they're very empirical. So how do I use this lesson? Okay, it worked for this event. How about the next one? How about a different area? And so the way to go forward in my mind is to apply mechanistic models that are calibrated against semi-empirical data, against the field observation. And this is what we did for runout here. So what we see here is a very simple model of basically the resistance of the material that has failed now. So this is now the frictional resistance of the material associated with the runout. And so this is a Voelmi model. Basically there's a frictional resistance, and also there is a component of friction associated with the viscosity. And we applied this very, very simple model simply because we want to apply it for all the landslides, for entire areas. So it's simple enough.
2 minutes more.
Absolutely. Simple enough and still not, still go mechanistic based, which I think is important. So what we did is for each of those landslides, we do inversions until we find the parameters that match that landslide to the observation. So you can imagine doing that for the entire coastline. Here is just a simulation of showing this. And on the left you have basically what has been mapped with a model of the polygons, and the gray is what is modeled. And I'm not showing you the good matches here, I'm just showing you just random matches, these random simulations. So at the end we do inversions until the model matches the map. And so we're able to extract parameters, the Voelmi friction parameters, for each of those landslides, and look regionally the difference. And so in general, we find this model works very, very well, especially for landslides. We're able to estimate the dry Coulomb friction and the viscous turbulent friction that is necessary to match this runout. And then also for the very smaller landslides, we're seeing that this model is actually very predictive. It's biased, it's not matching the data very, very well, it's actually flowing too much, even for high friction. But you can use these insights for future simulations, and also when it comes to precipitation, use landslides. As things get wet and these parameters change, you can track them. That's something else to work. As I finish up here, I just wanted to make sure that you, because I'm still running out of time, you can do this now. Once we have these calibrated models, we can have predictive analysis. So I'm here showing here a flow chart. If you know what the seismic model is going to be, what the PGA is going to be, what the PGV is going to be, we can run this model in prediction mode, calculate landslides. Once they trigger, you can actually see how far they run and use that in decision. The predictions are not going to be super accurate, but then with monitoring, you'll be able to close that. In conclusion, I want to make sure that I communicate what I think is very, very important is to really achieve community resiliency. We have to be thinking of the system first. We have to start big and apply models like that. And of course, there is always going to be room for more sophisticated models on the high priority areas that we have identified in an objective manner. Advances in monitoring technology, and I'm showing here specifically satellite and UAV data, but we have integrated geophysical data and other data, do allow us to really have a very detailed documentation of what's happening from an earthquake, and I showed you the example of the Lefkada earthquake. And this monitoring data can work very, very well with numerical models that are also developed to operate at the system level. And I showed you a couple of examples of that for landslide triggering and landslide running. And I think once you start building your confidence in models like that, you can actually now more reliably predict and really be prepared for future earthquakes or even precipitation events. Although my focus has been here. With that, thank you very much for your time. I would like to acknowledge the PhD students who are always doing the hard work behind this work, my senior collaborators, and the agencies that funded this work. Thank you very much for your time.
Excellent presentation. Please stay back.
We now request the chair and co-chair to present the speaker with a memento as an appreciation for his talk.
So, we now have last presentation. May I call upon Dr. Ajay Chaurasia from CBRI Roorkee. He's going to speak on From Fragility to Resilience, Multi-Hazard Risk Assessment of Indian Himalayan Towns.
Respected Chairman, Co-Chair, distinguished guests, ladies and gentlemen, and boys and girls. Indeed, it is my pride and privilege to be here, and for that purpose, I would like to thank the organizers, particularly Professor Ashish, Dr. Anil, Dr. Murthy, for giving me an opportunity to be here and showing love, affection, and to speak about something on the topic that is on fragility and resilience. The today's subject matter I want to highlight is on Indian Himalayan town and followed by the multi-hazard risk assessment methodology what we have focused on. So whenever you talk about Indian Himalayan region, so basically it is stretched around 2,500 kilometers long, average width is around 1,500 kilometers wide, accumulating around 5.8 lakhs square kilometer land, which is 16% of total land of India. It is comprising of 13 states and 5 international boundaries associated with accumulating 50 billion people and providing half of the Indian population the indirectly it is helping in the terms of water resource, biodiversity and climate resolution. When you come to the geology of this particular land is young mountains, fragile mountains, geological perspective, with steep terrain, active from landslide, earthquake and different hazards like loss and debris flow particularly. And that is basically a cascading effect. Now, when you talk about the risk, which is nothing but a product of hazard, vulnerability and exposure, and definitely we cannot predict or exactly calculate the hazard, but yes, we can predict it. But as an engineer, we need to focus on vulnerability and exposures. So basically that can come from basic objective is to protect the people and habitat, infrastructure, those life safety and reducing the economic losses is prime focus. So vulnerability is my first objective because whenever you see different disasters happening all around the globe or particularly in IHR, so that is basically focusing causing a lot of loss of life, property damages, business losses. And the recent one on August 5th, 2025, around 40 days back, this kind of a disaster happened, which is a debris flow. It is Tharali village in Uttarakhand, North India. It is located around 2500 meters above mean sea level and gentle slope. The houses are sitting there and followed by the steep slope up to the height of around 4100 meters above sea level, and which is basically a foothill of Srikant glaciers. So that is a total difference of around 2100 meters, and from where this kind of debris flow terrain because of excessive rainfall. So this is the debris flow picture before, during and after, which clearly shows that what is the amount of extent which has happened within that around 30 to 40 seconds. Okay. Now, when you see this is the Tharali, and what is happening, basically around 150 plus buildings composing various kind of residential, hotels, including the heritage has vanished beneath the debris, and with the debris amount to lakhs of cubic meter, and with a depth at the leeward side around 45 feet. The similar scenario happened after 1 hour of that particular incident around 2:40 p.m. at Harsil. You can see the before and after effects. Same thing happened in Sian Chetty on the same day, but only the problem is something different, that there was a debris flow and it has been on the downstream of this particular town, that is Sian Chetty, which has created artificial lake, and as a result the entire village was inundated up to 6 meters or so. Entire bridge and all the roads were also inundated. Now I am coming to this from debris flow to the subsidy, ground subsidies. On 3rd January 2023, all of a sudden the houses in the town Joshimath in North India has observed excessive cracks happening in all the houses, resulting the excessive amount of discharge of underneath water, because this entire town is sitting on morainic deposits. Now, as a result of that, immediately we have visited the site, then observed, instrumented each and every building, and observed the crack happen, the way the cracks are happening, and then classified different buildings in usable, access further, unusable, and demolished. And definitely, the last two categories we have provided rehabilitation. For that purpose, we have adopted the MSK intensity map, and it was correlated with the crack classifications on the each of the building. There are around 3,000 buildings or so. This is the picture which has been created within a week after the ground observations, and which classifies the different building setups in different classes. Subsequently, another map, risk map of Joshimath was prepared. Later on, it was integrated with different geological, geotechnical, geophysical and building damage classifications, and thus this particular landslide microzoration map for Joshimath city was prepared, and now the city's development is happening with a very systematic approach, including retrofit and rehabilitation of the region. So from now, moving from landslide and down to the earthquake, so now India also revising its seismic zoning map. This is the draft seismic zoning map, which clearly shows the entire IHR region is in seismic zone 5 and 6, with the PGA value with the written period of 2475 years as 0.5 G. And when you talk about the earthquakes, we have witnessed several occasions and we have a great understanding. But now we need to translate this understanding into reality on ground. Having known the different kind of disasters happen on the foundation, masonry buildings, on the RCC structures, not only in India but globally, you can understand this is the prefabricated, precast buildings. Then the precast buildings which were constructed in India, in abroad, important lifeline like bridges, tunnels, dams, power stations, communication tower, and railway tracks. Not only the structural things, but non-structural elements are also important. Not every earthquake is a witness to that. That excessive facade in terms of glasses also lead to falling hazard. Now we should take a lesson from Taiwan. When we compare two earthquakes, that is 99 earthquake and 2024 earthquake, you can see the difference in terms of loss of life and property. Loss of life reduced from 2,400 to 18. Building injury reduced from 11,000 to 1,000. And cause or reason behind this, the preparedness and rehabilitation and mitigation measures. Keeping in all this view, it is commonality what we observe in excessive loss of life and property, particularly buildings and other infrastructure. And with this particular objective, we have undertaken to develop a methodology for risk assessment, multi-hazard approach for some of the 6 towns in Uttarakhand and Himachal Pradesh. These are the 2 states of India located in IHR. And for that purpose, we have carried out detailed hazard assessment, vulnerability, exposure, and thereby assessing the risk in terms of fatalities, injuries, casualties, economic losses, and building damages. And develop a risk donation map for a town. So whenever we come across to the Indian Himalayan region, the challenges associated, as we know, that having high seismicity, historical devastation, vulnerable population, and the anthropogenic pressures. In addition to that, when you talk about the hazard, we know that the complex lithology, lineament faults, geomorphology analysis, and complex natural setups need to be understood properly. Having studied all these aspects, along with that, we have correlated and studied in depth the seismotectonic map of India, past earthquakes, then Indian standards, which is about to come. All these aspects have been considered for in terms of geology, threats and fault information. Then this is the earthquake and liquefaction zonation map. So this is as regards to the hazard. In terms of vulnerability, we know that around 85% plus buildings are non-engineered, masonry buildings. Masonry being a heterogeneous material, poor performance in earthquake is well known. In addition to that, it is adding fuel to fire like steep slopes and poor sitting is a highly considered phenomenon. All critical infrastructure like schools, hospitals and important buildings are located at vulnerable locations, and particularly in the masonry, again it is an alarming scenario. So that need to be studied in terms of physical vulnerability, which basically attracts the social and
economics will spend. So for that purpose, we have developed a methodology which follows the two approaches. One is the detailed and fragility curve. In the detailed approach, we have conducted the detailed investigation of each road to survey of the building and thereby developing the economic loss-inducing parameters and factors in terms of penalties, wherein we have considered setting very, very important from geological perspective, then foundation, architectural and other parameters, assign them appropriate penalty, and it has been validated with reference to the past data of earthquake records in Indian context, and thereby calculated the earthquake feature index. Now, next approach also we have followed is the fragility curve development. The fragility curves were developed again for the Indian typologies using selected 11 earthquake records from PL. These records were scaled up and the analysis was carried out at an increment of 0.05 G up to 0.7 G. And thus by conducting non-linear dynamic analysis on different Indian typologies, we could develop the fragility curve map for masonry buildings and similar to that, the RCC buildings. These curves have also been analyzed and validated about their correlation. When we talk about exposure, so that is effect due to any kind of a disaster on population and asset is very, very critical. And then when you see the challenges in terms of exposure, the high risk population is at high risk because around 50 million people are staying over there. Then dense cluster, asset and infra is at vulnerable stage, and around 25% population comprised of a vulnerable population, less than 18 or 60 years plus. Having completed or collecting the data, we developed a model which basically assesses the risk in terms of fatalities, injuries, homeless, economic losses, loss of buildings for the short term and long term. And for this purpose, we have developed a damage probability matrix in terms of death and injury. Similarly, the loss of buildings for short term and long term. And this is the one of the case study I would like to present, that is for the Kandagar town. So this is the Kandagar town in Himachal Pradesh, which is located around in 26 kilometers, 26 square kilometers with this kind of a demographic setup. For this purpose also, we have again conducted a detailed investigation for each town from earthquake point of view, from extreme rainfall and followed by the probable landslide and other aspects. Again, you can see the pie chart which clearly shows that there is a good correlation between both the approaches what we have adopted in this particular method. This is the risk map which shows the damage states of the buildings, individual buildings in this particular town and which is posing to different risk levels. And this is the summary of different kind of damages or losses which what can have in terms of fatality, injuries, casualties, economic losses and short-term and long-term building losses. And that has been evaluated for different PGA levels right from 0.3 G to 0.7 G. Upon completing these facts and figures, we have plotted this data on a map which is with a 200 by 200 meters grid in terms of fatalities, injuries, casualties, economic losses and thereby the risk map for that particular town. In this, we have also highlighted the regions where we should establish resilient center that should be accessible in the post-disaster event and it should be robust so that it can provide the facility to the occupants or people there. So this is how, if we adopt the approach, definitely we can reduce the risk, and with that our vision was that today whatever the losses or risk losses are happening in terms of life and property, we need to reduce it by 2047 to around zero tolerance to this. And for that purpose, nowadays, whenever any disaster happens, recovery takes around 5 years. We need to reduce it to 5 weeks maximum. For that purpose, the mission would be the code compliance,
implementation is at the stage, then this informs us safe and land use planning, institutional coordination, community awareness, disaster risk reduction, mainstreaming, and important thing is fostering research, development and innovation. Now, what to do? For this purpose, whatever the construction will happen, because in all the disasters we have seen the community is your buildings, infrastructure, and the objective is to reduce the life and property and economic losses. So, our submission is that whatever the new construction will happen, that has to be taken place using confined density, which is well tested. What will happen to the existing building? We need to retrofit such buildings on a massive scale, primarily on phasing out these things. First of all, the important buildings using innovative technique, that is the steel twin lintel band. So in this particular technique, we have to simply provide the MS flat at the lintel level for low seismic zones, that is seismic zone 2 and 3. And in case of moderate to high seismic zones, we have to provide this MS flat band at lintel level, sill level, and at the corners in terms of an angle. Now, what kind of, what quantity or what should be the size and shape of this particular angle, that has also been evaluated experimentally as well as numerically, and that has been tabulated in this form. So for different stories, 1 to 4, in different seismic zone, wherever your building is falling, you have to pick up that particular matrix information and provide that those details in your. So this is a prescriptive kind of thing we have created based on our detailed experimental and laboratory investigation. So this kind of approach will only lead to saving, but again, it will terms will come. What will be the cost? So cost is also reasonably very less, around 3 to 5% of the reconstruction cost, which sounds good as against the 30% permissible limit provided world over for retrofitting. So in conclusion, I would like to mention that we have to focus on towns, buildings, and we have to give a multi-hazard approach, and for that purpose, the method developed will be of great help in reducing the risk in terms of loss of life, property, and making massive population exposure and create a severe impact, economic impact. Now, our basic focus is that future risk, which is escalating, we need to reduce it further. So, I am sincerely grateful to organizers, particularly ISSMG, IGS and IIT Bombay for inviting me here. And my special thanks to Professor Ashish Juneja ji, Dr. Anil Joseph ji, Dr. Murthy, and thanks to Government of India and you all for your kind attention and patience here. In the end, before summing up, I would like to invite you to CSIR CBR and Roorkee, from where I belong, for the 4th International Symposium on One Health and One World. So this is happening on November 2022 at Roorkee. Around 300 participants are there, 250 research-based publications, and a lot of exposure to the multi-hazard scenario, particularly focusing on IHR region. So I welcome you all for this event, and thank you once again for your kind attention, patience here. Jai Hind. Namaskar.
Thank you, sir. To present a memento to the speaker, Dr. Ajay Chaurasia, I invite the chair and the co-chair. Thank you, sir. Thank you, madam. And now to present a memento to the chair and the co-chair. Okay, sir.
I think all of you agree with me that we had 3 excellent presentations. The first one on, smart tunnel boring. The second one on big data analytics for post-seismic landslide. The third one on multi-hazard risk assessment of Himalayan towns. And first of all, I wish to congratulate and thank the entire team of the Geotech Asia 2025, and especially Dr. Anil Joseph, Dr. Ashish Juneja, and Dr. Dasaka Murthy for all the good work done. And now I request Dr. Akanksha to make a summary of the presentations.
Okay, so we had three interesting lectures, well-timed presentations. The first presentation was by Professor Derek Chen on Smart Boring Tunnel Look-Ahead System, Non-Intrusive and Economical Geophysical Investigation. The second presentation by Professor Dimitrios Zekos. It was on big data approach towards co-seismic land for community scale resilient frameworks. Indeed, the need of the hour. And the third presentation by Dr. Ajay Chaurasia from CBRI Roorkee for highlighting the recent major landslide and debris flow and the Joshimath subsidence event that occurred in the Uttarakhand state of India, and which also made the headlines all over the world. So thank you for such interesting presentations, and thank you for the organizers and the audience for being with us.
Thank you, sir. Thank you, madam. I now request Dr. Unikrishnan N, the organizing committee member of Geotech Asia 2025, to present a memento to the chair and the co-chair. Thank you all. Distinguished delegates, during the next 1 hour we have a panel discussion by the ISSMG board members. While the arrangements are being made, we have an announcement. The joint ISSMG Heritage Time Capsule and the Corporate Associates Presidential Group session will be held today, 10th October 2025 at all day, all night room from 2 to 3:30 p.m. Kind attention, the joint ISSMG Time Capsule and the Corporate Associates Presidential Group session will be held today, 10th of October at the all day, all night room from 2 to 3:30 p.m. The theme is Geotechnical Industry Footprint, Reimagining the Boundaries of Our Profession. This session brings together global experts to reflect on the past, evaluate the present, and envision the future of geotechnical profession. And right now we have a panel discussion by the ISSMG board members. The topic is past, present and future of geotechnical engineering. The moderator of the session is Graham Sholay. Panelists are Marwan K.M. Shahian, Chaidu Rigby, Ms. Daniel Kalak, Mr. Ash Cooper, and Hugo Acosta. I request the moderator, Engineer Graham Sholay, to take forward.
Good afternoon, everybody. Welcome to this panel discussion discussion, soil mechanics and geotechnical engineer, past, present and future. And this is a panel discussion with members of the ISSMG board. And most of you will know that the ISSMG represents about 90 member societies around the world, of which the Indian Society is one. My name is Graham Scoley. I'm the ISSMG board member, BP for Australasia. And I also work with WSP in Sydney, Australia. I'll quickly let the members of the panel say who they are, very, very briefly, and then I'll explain how we're going to run this panel discussion. Hugo, please introduce yourselves very briefly.
Hello everyone, my name is Hugo Acosta. I represent the Heritage Time Capsule Project and I come from Australia.
Good morning, my name is Daniela Polak. I'm from Chile, South America. I'm a appointed member and also I work with Pierre Delage in the Geotechnical Borders. I'm a geotechnical consulting and mining permits.
Good afternoon everyone, my name is Ash Cooper. I'm the chair of the Young Members Presidential Group from ISSMG and I've been a practitioner for the last 10 years.
My name is Marwan Shaheen, I'm a professor of geotechnical engineering. I am the VP of ISSMG for Africa, and I'm very honored that
And I'm Yuli, I'm elected member of the board of the ISSMG.
So we're going to have 3 questions initially that we're going to be responding to under the theme of past, present and future, and each question will try and wrap up that theme. So I'm going to ask the questions and I'm going to give one of the panel members about 3 minutes to respond to that question. There'll then be some maybe follow-up comments from the other members of the panel. So we'll go through each of the 3 questions and thereafter we will have about 20 minutes, I suspect, for comments, questions, contributions from the floor. That's how we're planning to run this session. All right, so the first question. So many of you will recall the panel discussion on Tuesday, which was related to climate change. And this question is a follow-up from that. Further to the panel discussion on Tuesday, which discussed climate change and focused on design mitigations, what can geoengineers do to help us mitigate the impacts of climate change proactively? Hugo, I think you were going to comment on this one first.
Thank you, Graham. Yeah, I think there's been quite a lot of examples that we have more extreme events more frequently, and climate change, if there's still people skeptical, it's happening, there is evidence for that, and I think the main issue, and it has been mentioned before, is that the reactive methods, they're not going to work, so we need to be proactive in the prevention of the effects of that. I think the main areas that we can contribute could be first policy making, because I think at the planning stage is when we as engineers and geotechnical engineers can influence most how the solutions develop, reducing the cost, making environmentally friendly, socially acceptable, and all that. I think there is still a lot to do in optimizing solutions. Sometimes I think that the profession is becoming more and more conservative. Even though we have better tools, we have better data, still we see people doing the same designs of 20, 30 years ago, and I think there is a lot of room for optimization, especially if we need to design for higher wind loads, higher earthquakes, more rain, more potential for flooding. So there is an opportunity there. I think in many of these issues we have seen that there is value in collaboration, and we need to come together just to make sure that we have a unified effort to tackle with this problem, because there's no point in people doing the same in different regions, but yeah, we need to collaborate and especially bring up to a higher level some of the most developing countries in terms of prediction and preparing for that. So yeah, I think that's like the main issues. I think policy, education, learning from failures also, and yeah, just sharing information between the profession in different regions.
Ash, would you like to add some comments to that, please?
Yeah, because it's, those of you who are in the audience are 35 and under, it's you or who will be dealing with a lot of these problems as we go forth in our careers. And on Hugo's point, I think challenging our colleagues in other engineering disciplines is going to be extremely important as well. You know, we all know we are the foundation for whatever goes on top, so if we're pushing ourselves harder, gives us good authority and grounds to be pushing our structural colleagues a little bit harder too, especially in carbon reductions, nature-based solutions and things like this. So they're all great things that we can help reduce, like climate change proactively going forward as well. I remember a saying that was told to me very early in my career was, dirt is cheap and easy to move, structures are very hard and they're for life. So, you know, before we go and build, you know, solid carbon heavy infrastructure, we should always be thinking twice if there's other options around it. Codes quite often constrain what we can do, and particularly the term resilience. You know, in this, everyone has a different definition for resilience, and there's sort of no unified meaning around it. Could we build back quicker, or do we build things stronger? I don't know. And there's been great examples and great just catastrophes of both cases. Going proactively, getting ahead of the curve, I believe it starts with really pushing ourselves and going, do we need to build something out of concrete here? You know, do we need to do something like piles? Can we incorporate the topography and terrain that we've got currently rather than building some giant bridge over the bottom, over the top of it, or piles or something like that? So, yeah, it's sort of a bit of a roundabout way. Yeah, I think really challenging each other is going to be the key to reducing things overall in our carbon influence.
Thanks, Ash. Would any of the other panel members like to comment? Would you like to comment?
You will, especially if you do lots of nature-based solutions.
I think what we heard in the morning from Dimitri, adapt the new technologies because they can predict, and we can also input in the algorithm preparation for climate change, because we can read the past data and project it in the future. So models like Dimitri's are priceless, and you know, data is in our hands, so we can use it to cater for climate change.
You had a wonderful lecture.
Thank you.
Yeah, so I'm from IIT Bhubaneswar.
My own thoughts on this topic is that I feel that we talk a lot about resilience, and we talk a lot about design mitigations and so on, which is obviously going to be critical in a world where we need to continue accommodating population and growth and so on. But I do think about smart ways of doing things, and there have been some presentations at this conference. Alternative technologies, alternatives to cement, which we all know is one of the highest producers of carbon emissions of the materials that we use. So I think more research and implementation is critical from us as geoengineers, and persuading our clients of the importance of doing that. In Australia, there are some government organisations that are putting expectations on the use of certain materials and really targeting reduction in the use of concrete, cement type products. Okay, so we'll move on to our next question. We will be coming back later, as I said, for the audience to participate in some of these questions. So the next question, again, thinking past, present and future. Present is that AI is with us and machine learning is with us. Now, how far can AI and machine learning take us as geotechnical engineers? But going beyond that, because AI is with us now, what do we still not know or haven't solved that define the future of geotechnical engineering. Marwan, maybe you want to start responding to this question.
Okay, we as geotechnical engineers pretty much rely in many situations on precedents and available data measured in the field or in the lab. So this is why we get a lot of empirical operations that develop by regression analysis of existing data, laboratory and also field. But we used to use these equations, knowing the limitations of these equations, knowing the limitation of the size of the data that used, the limits of the data that used to develop those empirical equations. For example, one example of if we have a wall, deep excavation, and in this deep excavation wall, what kind of pressure that will be applied on this wall by the earth? Is it active? Is it passive? Is it K0? Okay, it's actually none of those, and we usually rely on the measurements and empiricism. And this is why classically Professor Peck developed air and earth pressure charts in 1969. Now, those charts, can we use them to predict the straining actions on a rigid wall of the underground stations of Metro Line with a 1.2 meter reinforced concrete diaphragm wall? It's very, very rigid. The answer is no. And this was happened. What happened is during the measurements of earth pressures on these, we found out that no, we have much different earth pressures than what we had in Peck. The reason is that Professor Peck's chart was developed based on measurements on Berlin walls, which are flexible walls. So knowing the limitations is very important. Now, similarly, dealing with regression and empirical equations, we can deal also with AI and machine learning. As long as a geotechnical engineer know the limitations of the data, the limits of the data that we are using, we respect that, then we can succeed with using these tools. And actually, so the key point is to know the limitation. Basically, these tools are very useful in terms of helping solving some problems, maybe sometimes complex, but these tools cannot replace the judgment, which is a very essential tool in our geotechnical profession. Judgment is an important tool. Can AI replace our judgment? I don't think so. The question that is open now to us, how can we deal with AI and machine learning as useful partner in our profession, rather than having them as basically a black box, using them as a black box and that we don't know what's inside. This is the question. Thank you.
Thank you, Marwan. Ash, did you want to add to that?
Again, it's mine and all of you young people here's future, so it's important that we talk about these things. On Professor Marwan's point as well, as we all know, with any of the models that we all use, FLAC, Fluxus, Abacus, whatever, you put rubbish in, you get rubbish out. So we need to be very mindful about these black boxes and what we're doing with them. And coming into the question, how far can we go with AI? We probably need to recognise where we are right now. And if you think about how long a piece of string is, it's kind of the question we're at. And we know that the piece of string is going to be equal length either side from the middle. So as long as we know where we are in the middle right now, we can see where we're going, how much has it changed our industry so far. I think it's had a profound impact. But it's been more about how do we reduce the current time and effort that we are spending on, rather monotonous tasks to allow us to go and do more things and explore more things. And the lecture earlier this morning about the landslides was a perfect example of that. But the fundamental piece, regardless of how good that AI model is going to be, the fundamental piece about capturing field data accurately and using multiple methods so you can check the discrepancies and differences between it, and then inputting that in, that is the most important part. If we leave it to some other method that is not tried and true and we don't know anything about it, then how are we supposed to appreciate and rely on the results that these models are going to be producing for us? And I'm sure we can all agree construction is quite an age-old industry in itself, and we've been moving towards almost like a revolution, if you like, with construction for some time. It probably started with automated compactors and machines on site. They're all learning by doing things. So we're probably all a little bit scared of where we might go with AI. I know I certainly am. Lots of you here have had illustrious and long careers, and I can't say for sure that mine will be the same if AI moves at the pace it does. So, I think we're just going to have to be here for the journey and implement and learn from the lessons of the past, which you've all paid for us.
Yeah, I'd like to say something probably connected to the previous question is that, all these new tools are based on data. So a way that we can influence and contribute to limiting the impacts of climate change is really go deep into that, and sometimes questions are said, we need more data. Do we need more boreholes in a particular place where there is a lot of information, or do we really need to measure again the properties of a material in which the profession has been working forever? Yeah, so I think that's also a way that we can impact being more critical. I think that needs to come with what I mentioned also, changes to policy and standards and all that, because I think we're becoming very prescriptive on what has to be done, and they just do it because it's written somewhere for compliance, but at the end of the day, in many cases, it's not really necessary. So I think all the data that is feeding these tools, we should be taking advantage of that and trying to reduce the carbon footprint of getting more data.
Thanks. Does anybody else on the panel wish to comment? Lily, any comments?
Okay, so reading the question, and I'm going to throw the question to the audience, whoever is left in this room. What we haven't defined, and we heard this morning my lecture, and the person from Keller, sorry, I can't remember his name, is how do we tame human nature to follow the standards? This is something we need to define for the future of geotechnical engineers. So it's all right about predictions, it's all right about big data, it's all right about AI, but when it comes to constructing on site, the basic things go wrong because people don't follow the specification. So that's a question for the audience.
I'd like to pick up on a few points that were made by the panel members around design codes and resilience. I think this is a particularly important one where we're suffering the impacts of climate change, and we're finding that the design codes aren't really helping us to solve the problem. They are far too stringent for what we really need to achieve, and that's forcing us into spending a huge amount of money that we're not going to have available as a society to fix up things to standards which we are beyond reasonable, because we just need to fix things up so that they retain some resilience and can be rebuilt as quickly as possible, so that we maintain, in the case of transport corridors, connectivity and so on. So I think that's an important point. And a few other things that sort of crossed my mind with this question defining the future of geotechnical engineering, I think about, well, where are we going next? And we've certainly been to a few places today in some of these presentations, but where are the Himalayas and Greece and various other places, but where are we going next? And space, Mars, is that going to be a reality? And I know that Pierre Delage in the audience has already done some work in relation to geotechnical engineering for exploration in space. So I think that's a possibility. But I'd like to bring it back as well to something which I think is very basic at the moment in the past and currently. And I asked a question about whether we're still going to need to be drilling boreholes as part of the future of geotechnical engineering. We rely so heavily on some very basic tests, and we have heard again today from smart geophysical techniques to look ahead of PBMs, which I think is absolutely fascinating. But are those technologies that we're going to be looking more to in the future and trying to discount very rudimentary boreholes and standard penetration testing? So just a few thoughts there before we move on to our next question. And this is in relation to, I suppose, developing our young people. Past generations have learned from mentors. I know I certainly did. I remember my first day as a geotechnical engineer and the mentoring that I had from a senior person. We've learned from mentors and field experience, and new generations learn from data and simulations. How can we combine both worlds to keep the experience alive in geotechnical education? And I will just add that how can we combine both worlds to keep the experience and judgment alive in geotechnical education? Daniela, would you like to start responding to this, please?
Yes, of course. In this question, we want to know who is here. So I would like to ask, are you enter? Next.
Okay. Next one.
It's your turn. So the first question for you is, go on, Graham. How many of you are professors? One there?
Hands up. There's lots of professors here. Sure.
Professors, 3, 4, 5. Dimitrios, you're not professor. You changed it. 6 over there. Okay. So, over there are a lot of professors. Great. So, how many of you are mentors or currently working with a team of young engineers? Much more. Okay. And the third question is, who has gone to the field with the students and or young professionals? Okay, so I don't know if you saw that, like everyone, the first part of the question is already answered. All of us, we are doing that part, isn't it? So, but for me this question is like, do we have faith in the young society? And my second thought about it, yeah? We need to.
Can we get the microphone roaming, please? That microphone's in.
Hello. Good evening. Good afternoon, madam. Actually, we need to trust to our Gen Zs because they are very smarter and very sharp.
Yeah, absolutely.
And they are dealing with AI.
My second thought is about after COVID, there was an increase of the conference around the world and the interest in participating in that conference. And that makes me feel like as a human beings, we want to be and to share our research with each other directly, not online, not, we don't want to be alone. So I think that maybe we are seeing like they are only in a little cage, but it's not the human source of the movement goes naturally to be in a community, you know. So I'm very optimistic about it. And as a panel, we want to hear your experience about it. What do you think about it? So I invite you to share with us about it. Microphone is open.
We have a roaming microphone, so if you'd like to make a comment on this topic, please wave for the microphone.
I'll say something very short while someone raised their hand, but I think the question is how can we combine is good, but we must combine. I mean, we need to keep you're saying that human interaction of the traditional mentoring alive, because I think that will be irreplaceable.
Yes, please.
You asked us to share our experience about geotech and how we are connecting with the students and research organizations, right? So we are dealing, basically I am a professional superintending engineer in metro organizations. Generally we are having the PILE and metro works, major infra projects we are dealing with. And during works, there are, unlike situations, means situations are not always same in pattern. So sometimes pile depth and pile capacity, consultant conflicts, and they are not on same opinion. In that case, we are always approaching towards the research organizations. We believe, we actually trust on them. Whatever their decisions, one example of Metro Car Depot, Kasheli Car Depot, our consultant, our experts has given us for the 27 hectares ground improvement proposal. Our consultant has given certain proposal, which amounting almost 250 CR. But when we are in contact with IIT, we have done due diligence on that proposal. That cost is drastically came down. So likewise, during our professional work, if we connect with the research organizations, then we are getting benefit, means exchange of knowledge, and wherever we try to reduce the cost curtailment. As a government organization, is our duty that the cost curtailment without compromising the quality. That due diligence has been done with the IIT professors, panel discussions and various. So that professionally connect we are finding in geotech. Thank you.
Thank you. Anybody, I'm just seeing if anybody else in the audience has bring up their hand. You wanted to say something?
So the experience from the UK, how to keep the young engaged. So everybody's talking about AI, and of course the young generation is very good with computers and AI and machine learning. So there is a divided opinion in the education in the UK. Some universities ban the use of ChatGPT and from students for the homework, and some other universities force it and enforce it. So there is a university that the professor asks all the students to use AI to do their assignment, compulsory, and their job is, or their judgment on their essay, or their task is to critique the AI. So find the faults in the essay that the AI is going to do. And I think that's the best way, because we can't go away. AI is here to stay. It's a great tool, but that's exactly what the custodians and the professors in the room should teach the kids, use it, don't let it take over your life. You make the decisions, like Marwan said, but teach them that they need to use it because otherwise they'll be left behind. Like I read recently in China, they start coding from primary school. This is a subject for kids. So how, if they start at the age of 7 or 8, we can't just close our eyes and say, no AI. So yeah.
Thanks. Anybody else on the panel or in the audience? Mr. President.
Ask Google, how can I make more money? And ask the same question to ChatGPT. You'll see the difference of transition. ChatGPT will ask you, who are you? And then will guide you. Google search will stop, say, I don't know, gives you some business example. If you remember in class, at my age, we used to do square root by hand. And then the calculator came. I remember black and white TVs. Who would have thought that you would have now widescreen with this quality? And it's growing so fast that the answer to the question is only God knows. We don't know. I don't know if we still need boreholes, especially in urban areas, 20 years from now. If everybody's putting all the data in the AGS data input, you don't need boreholes anymore because you know 5 meters what you will discover. And this will decrease with time. So AI in the medical field is now ASI. Artificial super intelligence. Very soon we will not need to visit the doctor if you're feeling some symptoms. Yes, we want to get attached to engineering judgment, but I don't know if this will be. So I'm telling you how much I don't know, because I don't know what will. We can predict, but it's going so fast that I don't know.
Thanks for that. Walter?
Thank you. And let me to disagree. Of course, I am more with the Marwan point of view that we don't have to use the AI as a black box. We need to understand what is happening. If we have a very large amount of data, let's say for a city like Delhi or Mumbai, where it's very dense populated, perhaps we will have borings every 5 meters. That's true. But that's true for today. We're forgetting that the fourth dimension is all mechanics, it's time. So it's changing of time. They consolidate, they gain resistance, they decrease in compressibility. Perhaps they change their dynamic response, so they change. Even though we have a great amount of data today, it will change in the future. Perhaps not in a week or a year, perhaps in 500 years, but still it will change. It will not remain constant.
I disagree. That's why it's called artificial intelligence, because it follows you with time. I want to give you an example. It's amazing. I had a problem with a simple bulkhead and one anchor that failed. And to me, I had to do the math, and then did it by hand, and then did it all. I discovered that it's at the edge of, like, safety factor of 1 line, But I plugged it directly into ChatGPT. And he immediately said, this looks like Berlian's. I said, what? What's that? And then I kept playing with ChatGPT. And I said, give me the right answer. It wasn't right, but it was very close to what I really like to see. I'm telling you, it's going so fast. It's scary how the AI is moving. How do you And it's already scary how it moved in the other professions. So I don't know if we will still exist in 100 years. And here, the HTC project, that's why we're establishing it now. Smart.
Thank you. Anybody else on that?
I have a question here. The geotechnical testing and inspection, is that standard can be maintained throughout the globe, which help contractor or companies immediately they can start the earthwork?
Sorry, was that a question?
Every time whenever project starts, people start doing GTI, ground testing and inspection. They come with some data and some details, then they start doing the work. Before that, the international standards can be set as a benchmark of this area, this location, globally. This is the hardness. That data can help immediately to start the project. That's what I am looking at it.
I think what I heard there is that you're saying that at the start of the project we can start feeding data in, and that AI will then take that data and continue to build on it as we feed more data in. Is that what you're saying? I'm sorry, it's very hard to hear from up here.
It's too hard, but the thing is that some standard can be thought of bringing it.
Yes.
It's a request from our end.
Thank you. Any other comments from the floor? My own thoughts on this question take me back. Oh, sorry, Ash, you wanted to say something? Go ahead.
I was actually going to talk about patience. I should have waited then.
Yes.
Apologies, great. And Mark's example talking about doing square root by hand and then calculators and the TVs and everything now. We are moving so quickly, so I think patience and trust in each other between less young and young engineers is going to be critically important. Because if you don't have this, then how are you supposed to say, well, how do I know this model or this program or this calculation is right? Unless you're seeing it in a format and a way that makes sense to you. So, and having an appreciation for what's, we saw the professors put their hands on, having an appreciation for how these, I'll use very plain language, this very, very awesome, far greater than my intelligence, these things that the professors are pumping out of universities. How do we maintain our appreciation for that and also implement that into the field so we can carry on as well? And not everyone's going to see things the same way. We all need to be very, very patient and build trust with one another. That's one little bit. It's easy to look someone in the eye and shake hands and cool, let's do business, let's work together. I don't know if we have the same emotional connection with our computer. So I think that's going to be a really interesting thing we're already coming to the end with now, and it's only going to get worse as we go forward, and how we overcome that I really don't know.
It gives perspective on Ash, because it takes me back to when I started in this profession nearly 40 years ago. First day mentoring, subsequent years where I would go to sites with senior staff, peers, and I would be inspired by the stories that they would tell me about the projects that they'd worked on, small, large, all corners of the world, and that inspired me then to try and become a better geotechnical engineer. And I think about what my role is now, some 40 years later, and I don't want to use the words AI or machine learning or Praxis or anything like that. We're talking here about what I think needs to stay in the profession to make us good geotechnical engineers, and that is being inspired by those stories. And that helps as well through that experience to create what I think I contribute back now as a consulting engineer, and that's judgment. And I'll challenge anybody in this room to say whether they think that AI will be able to give us judgment in the future, because at the end of the day, talking about Mark's example there as well, of the single anchor, judgment. What do you really think from years of experience is going to happen here? And AI will try to give you an answer maybe to that, but I don't think it will give you the right answer. Demetrius, you wanted to say something, I think. Can we give the mic to Demetrius?
I disagree with that comment.
Okay, thank
Thank you very much. I was not planning to intervene, but actually, I think your comment is exactly right. Our goal in education is not to teach them the very capacity equation or how to, at what level, stress level something fails, is to develop the engineering judgment. And that only happens with hard work from the students and seeing beyond grades and seeing beyond this math. That, although aspects of it, calculations, can be copied and also used by AI, I strongly believe that it will be humans that will sign this. And eventually they will have to have full responsibility. And that's what I say to my students. I say, you can use AI for whatever you want, but whatever you put down on the paper, it's yours. And it's so easy on the text. We go to AI and copy geology. So I bring them to my office and say, okay, you wrote this, tell me more about this process. And if they haven't done the homework, they haven't thought this, they cannot say a second sentence about this type of aspect of geology, because it's not theirs. Same thing with the math. Occasionally they go with AI and they use a different equation, and I said, oh, okay, that's not what I gathered in class. Please tell me why you use this equation. Silence. What were the assumptions of that equation? Silence. That stuff cannot be reproduced by AI. Humans cannot use AI intelligence unless they have done the hard work. Now, if you have done the hard work, you'll be able to use AI, and that's great for you. But I think there will always be tremendous needs for what we actually do. It's going to be just different. I just want to make that engineering judgment is what we're after. And some of it can be reproduced by AI, but it's really at the end as engineers, we have the responsibility for this type of work. And I think that's what we're trying to teach to you. Thank you.
It's becoming interesting. It's becoming very interesting. So I disagree with you long term. I disagree with you long term. I disagree with you long term. I agree with you all. Within the coming 20 years, we still need our judgment. And you know my keynote lecture, it's the main subject, go to the basics. But what I'm looking at is 50 and 100 years from now. Now, physically, robots are better than us in dancing. Just open robot dancing with Boston Dynamics. What I'm seeing that there will be better engineers in engineering judgment 100 years from now. That's what I'm predicting. And I'm not confirming, I'm saying I don't know. That's what I want you to understand. I say 100 years from now, we will not know. We don't know from now, in my opinion, if the engineering judgment of the ASSSI, because it's going to be artificial super intelligence, collecting data from artificial intelligence, not from our human knowledge. We don't know. That's what I'm saying. I'm not saying you agree, you are right or wrong. I'm giving my opinion.
I'm delighted that we've inspired some serious debate here, and that's what this is about.
I love it. Oh, by the way, remember the governing basic equation? There will be geotechnical engineers only if we love soil.
We remember it well. Okay, well, we are now past the scheduled completion time for this session, which was 1 o'clock, and I'm sure that people here are interested in going to lunch. You might think I'm seeing lots of nods there. So I think we might draw this panel discussion to a close and thank our panel members for their contributions, and from the floor as well for what has been a most interesting and rewarding session. Thank you very much, everybody.
Thank you, Professor Grahamshuli. I now invite the moderator of this session to hand over the mementos to all our panelists. I request Dr. Mark Balaus, the President of ISSFG, and Dr. Anil Joseph, the Chairperson of Geotech Asia 2025, to join the distinguished guests on stage.
Could I ask all board members present to come, since we're here for a nice picture of all the board, if you allow? Dimitrios, Pierre, Albert, Andrew, yeah, perfect. It will be a nice picture. Let's move forward.
Request the moderator, Dr. Graham Sholay, to hand over the memento to Professor Marwan. Request Engineer Chaido Rigby to accept the memento. Request Daniel Apollo to accept the memento. Request Engineer Ash Cooper to come forward. And finally, Engineer Hugo Acosta. And I request the President of ISSMG and the Organizing Chairperson of Geotech Asia 2025, Dr. Anil Joseph, to present the memento to the moderator of this session. Thank you all. And now, ladies and gentlemen, we break for lunch. Lunch break is till 2 p.m. And from 2 to 3:30 p.m. we have the panel sessions. Thank you all. And now we break for lunch. Post lunch, we have panel sessions in multiple halls from 2 to 3:30 p.m. We will resume our sessions sharp at 2 p.m. in all the panel halls. And from 3:30 to 4 p.m. we have a break, tea coffee break. And thereafter, we will all assemble in the same hall for the Bright Spark lectures. So request everyone to make a note. We have the Bright Spark lectures from 4:10 to 4:50 p.m. Subsequent to a title sponsors note from 4 to 10 p.m. And from 4:50 to 5:30 p.m. in the same hall, we will have the closing ceremony of Geotech Asia 2025. In addition, please make a note that the joint ISS MG Heritage Time Capsule and the Corporate Associates Presidential Group session will be held at all day, all night room from 2 to 3:30 p.m. During the same time, we also have panel sessions going on in all the multiple halls. After the tea break at 3:30 to 4 p.m., we will all be assembling back here in this hall for the Bright Spark lectures, followed by the closing ceremony from 4:50 to 5:30 p.m. Thank you all.
पॉप करके रखो